All right, so let's see if we can warm up with this problem. So let's look at this problem. I don't know if you need a hint for this reaction. So we have ozone reacts with 3 equivalents of iodide and 2 equivalents of acidic protons to give us oxygen and the iodate and water. And so then we do this titration. So then so you could have written out this part, right? So just the titration here. All right, so now that you have this information, see if you can solve the rest. Yeah, you could do that. I don't think you need to do that to solve this problem, though. So this is just more like a stoichiometry refresher, kind of with all this stuff, but. So what do we get for this problem? Walk me through your process here. Yeah, I think it's sodium sulfite. Yeah, let's take it from there. So that was excellent. So right, seeing this relationship was good. And so now let's walk through the math together. So take our moles, multiply it by, or sorry, molarity, moles per liter, multiply it by our liters, so convert that to liters. So then we get 8.55 times 10 to the negative fifth moles, correct?
Yep.
And so then what's our relationship once we get moles? Oh, wait, I think you skipped that, right? Because we found moles of the sodium ch223 species, right? But then we have to figure out. Oh, yeah, so we have 2 to 1 ratio, so it's half that. So I'll write that out. So for our moles, and so we have for every 2 moles of that, we only have 1 of our iodide. So now 4.27 or 4.28 times 10 to the negative fifth moles. And so then if we read the problem, right? So we reacted a 43.15 gram sample of air. We're trying to figure out ozone mass percentage. So now we can get, right, mass of ozone. And so ozone's molecular weight, 16 times 3. I did some rounding. And so now let's take our moles and multiply it by our molecular weight. So then I get this many grams, so 0.00205 grams of ozone in our 41, what was it? 43.15, my bad. In 43.15 gram sample. And so now we can figure out mass percent. And so now we just divide and multiply it by 100 to get our percentage. So pretty small, but this probably matches, right, with ozone, the amount of ozone in the air since it's pretty small. So 0.00474%, or 476, sorry. And we could say gram per gram, just to be clear, since it's just a percent. Oh, the 48 was just the molecular weight of ozone.
Oh, okay,
Okay. Just making sure we're on the right thing. So I think we'll just go on with our review, because I'd put some of the cell potential stuff on there, but I think we'll just focus on review. So let's keep doing that. So let's start off. Sorry. Go back to my review problem. So let's try this one. And so we're looking at this dissociation of HF. And so I'll write it out at least. And so at 30 degrees Celsius, the dissociation of HF is 5.7 times 10 to the negative fourth. And so see if you can find the delta G. right, let's hear what you did. So what formula, what answer?
Since we have a temperature, we do have for dissociation, I chose delta G is equal to negative RT natural log K.
So that looks good. And then, of course, write the R is 8.314. Temperature, we know we have to be in Kelvin. So add 273 to that. So what is that? 303 for our temperature. So that looks good. So then solve. And then what did everybody get once you plugged it in? So do we get either 18,000 joules or about 18 kilojoules? Make sure I have the sign on that one correct. So 18.8 kilojoules there. Let's try another warm up or problem. So the solubility, product constant for aluminum hydroxide is 8.3 times 10 to the negative 32 molarity. So determine the gram solubility of aluminum hydroxide in a solution buffered at 10 pH. So how's this one coming along? What do we need to do to solve it?
So first, I know we need to set up the equation as far as this association. I know because we have a more basic solution, isn't there, I mean, I know that we're gonna have some hydroxides, yeah, somewhere.
So, yeah, so we can, I feel like we're there. So what's the problem though? So we can set up, right, our solubility product, right? So we can at least think about it as S and 3S. But then what's the hydroxide concentration dominated by? And I mean, you said it was basic. So then what number do we need to calculate first then? Yeah, so the POH. So let's do that. So what's our POH? Or,
pOH should just be 4.
and then, so let's find our concentration then. So 10 to the power of -4. So now that's our hydroxide concentration. So 1 times 10 to the -4 for hydroxide concentration. And so now we're good to start plugging it into our solubility expression. So write out your reaction, and we have our dissociation, of course, with our 3S. And then now we'll plug in, though, our actual kind of concentration, so our initial conditions. So, right, we initially have 1 times 10 to the -4th concentration of hydroxide. Then we need to do, right, our equilibrium change. And so now we can add these expressions, or kind of write what's our change. So plus S plus 3S. So this is more my side work setup. And then equilibrium. So now S, and then 3S plus our hydroxide concentration. And so might want to set up what our KSP was. So that would be, right, our aluminum concentration times hydroxide cubed. And then that equals to this tiny number. So probably going to be an assumption later. And so now we can start plugging all of those expressions in. So we have S times our 3S plus 1 times 10 to the -4 cubed, right, because that has to be cubed from our expression, from, right, our KSP up here. And then that's equal to that 8.3 times 10 to the -32. And so there's our hint for the simplification, right? So we can get rid of this 3S factor in the plus, since again it's going to be dominated by the hydroxide anyways. Again, with that very small number. And so now we're left with S, and 1 times 10 to the -4th cubed is equal to our expression. So now solve. So then we get our S is 8.3 times 10 to the negative 20th. And then that's in molarity, right? And then I think it asks for gram solubility, so gram solubility, we just need to multiply it by our molecular weight. Does anybody have that handy by any chance? So moles per liter, so times ask Google. Aluminum hydroxide, unless someone wants to add it up. Oh, Google says 78 on the dot for it. So grams per mole. So then that gives us a 6.47 times 10 to the negative 18 gram per liter solubility. So still pretty small. So questions about that one, you will have one on your exam, just like that one, just probably at a different pH.
Where did you get that concentration of OH in?
So it came from the pH, remember? So then we started with the pH, and then we used the pH plus POH equals 14 relationship, got the POH, and then you take 10 to the power of your POH to get the concentration, or 10 to the power of the negative, sorry, pH. Yeah, so just watch for that pH on your exam, and it'll probably be a similar process.
What happens if we have an acidic pH and we evaporate the like hydrogen and then cancel out the OHs that have the lysines?
We probably like wouldn't do that, because right then you'd have to calculate how much would be consumed, right? Because then it'd be more like how much can your acid consume, so how much hydroxide would it neutralize, and then that would at least like have consumed it that much. So yeah, that won't be on there just because it gets too, it'd be like too many steps, so it'd be kind of convoluted to ask and for you to calculate. Yeah, because you just consume all the HCl till you made a neutral solution, and then it depends if you're going to keep dumping in aluminum hydroxide or what. Let's see, so we'll take a little break from the math for a second. So you have assigning oxidation states as well. So let's do some practice of that. So this one, assign oxidation states to all elements. Then I'll also draw the next practice. double check. Is that your final rule?
Just because you got yes, I don't yes.
Yep. Yeah, once you're done with the top, see if you can figure out the structure as well. Ah. Yeah. Yeah, I can't draw.
That makes more sense. I was like, that carbon looks a little negative from that.
Are we still working on the bottom one, or? All right.
You gave me someone else's.
Oh, sorry. Yeah, so anyone that is like right, every point's a carbon, and then that's a carbon, so all these are carbons. And then the extra lines are double bonds.
Just make sure carbon has 4 rings. Yeah, 1 hydrogen for each one.
Yeah. I was wondering what I had done, if it was gonna be 9 out of 20, 9 out of 100 to begin with.
Yeah, thank you. Feels like I maybe did some math.
Just like that, your dreams come true.
Oh yeah, I have 2 nameless KSP homeworks. When they're completion, they look complete. Are you sure they don't look like your handwriting? It looks like some girls.
Wait a minute, that one's not mine. That has very similar handwriting to me. That other one,
Could be yours.
the other one. Yeah.
I know, they actually look really
I
similar.
know.
Yeah.
I thought that one was mine. Oh my god. Do it.
Okay. The other one's still homeless for now. All right, let's at least start hearing what you got. Oh, we need more time. Okay, I'll give more time. So what do we get for the first one? We have this vanadium trichloride species within these tetrabromides complex. So this is, we didn't talk about it too much, but this is implying that this is what's called like outer sphere. So basically, like the vanadium, and I don't know the geometry of the vanadium trichloride, I'm just kind of assuming. So this would be probably more complex like that, and then these bromines would be hanging out, more like outer sphere, like we're used to, but that doesn't change your oxidation state. So what do we get for bromine?
That would be, I believe, -4 for all four of them, and maybe -1 for oxidation.
So -1 for all our bromines, and then what do we get for chloride?
Probably also negative 1.
So also -1 for a halogen, and then what does that leave vanadium? So +5, and that makes sense. So if we were to find our periodic table, which now I have lost. So vanadium, right, it's in there D5, so it can behave like 5, so as long as it's not beyond 5, then that's probably reasonable.
-7 plus 5 equals -2, so that looks good as well. That chart.
And then what do we get for this complex then? So let's start with our carbons. And so of course you have to draw on maybe some hydrogens.
I got -1 for the first four on the left.
So
That are all bonded to the other carbons and the hydrogen.
excellent. So all those carbons are -1. So kind of the trick there is they're all bonded to other carbons, so all those get split. You don't worry about that, and then you're just kind of looking at that hydrogen and carbon comparison. So carbon gets the electrons if we pull it off. And then what about, let's start with this carbon. So what's its oxidation state? So +1 as well, so still split. And so we could kind of see that. So right, the electrons go to sulfur, and then these get split 1, 2, 3. So 4 minus 3 is +1. And then what about sulfur? And then I didn't draw them, but you should remember that sulfur has, right, 2 lone pairs, and then you pull it off, and it got those electrons. So what do we get for the oxidation state?
So the sulfur is connected to a carbon on the other side, correct?
Yeah, so that's a carbon.
So I could be wrong on this, but I got 2 -2
Yep, so it should be -2. So I kind of drew it over here, so 6 minus 8, so -2. And then let's look at our nitrogen before we look at this carbon. So we have nitrogen, and so it probably also has a lone pair. I didn't draw. So what happens when we pull it off? So it's more electronegative than carbon. Yeah, so it gets all of these. So it has 2 that it had, then 1, 2, 3, 4.
So it pulls 2 from the one carbon on one side, then one carbon, or one electron from the carbon on the other side. So that would make that 3 minus?
Yeah. It should be 3 minus. I don't know if I followed what you said, but yeah, 2 from this one and then 4 right from that bond. So it took all of the electrons. And so then if nitrogen is 3 minus, and then we have this poor carbon over here, so what is its oxidation state? So +4, right, the sulfur got it in this bond, sulfur is going to get it in this bond, and we already said nitrogen got all those. And then what does that leave sulfur's oxidation state at the end?
2 minus.
So 2 minus, and then hydrogen, so 1 plus again there. Questions on that one?
halogens, I was a little confused with that because I know with some of the rules, like certain halogens, like say fluorine, for example, we can already assume that it's gonna be a negative one. But what about some of the other halogens? Can we just assume that they're gonna form like negative one, or?
Yeah, they'll usually do -1, especially like in these metals. It's the only time they probably wouldn't be formally -1 is if we think back to some of the weirder compounds, like II3. So that one is going to have, right, iodine in different oxidation states.
But as a general rule of thumb, it should be kind of basically they're gonna be a negative one.
Yeah, yeah, especially when paired with the metal, right? So the metal is usually always the one giving up the electrons, and so, yeah, the halogen's going to follow that trend of accepting that one electron.
Okay.
Oh, I just realized we skipped this little guy over here. So then it got, yeah, so this should be a 1 plus. You're right. So, right, all those evenly split, and then nitrogen got those two, so 1 plus there. Yeah, we'll have, you'll have one metal one like this, and then one organic one. So I don't know if it'll be as ringy, but yeah, another organic. So let's see. Sorry, I'm looking at both your review and your test to kind of see what I haven't covered. So let me know what you want to cover, because we're like slowly running out of time. So your exam is going to have a solubility question, so kind of what happens with this substance in the different conditions, so like maybe salt or different ions, so what happens. And then there'll be something, so let's go back to our Gibbs chapter. I'm trying to find that chart that's helpful. Oh, here we go. So basically, right, like this sort of thing where you have to kind of predict based off of this equation, you know, what are the signs, what's going to happen, will it be spontaneous? So there's going to be a question like that, just like it'll give a scenario. You know, it could say if this reaction is like endothermic and spontaneous, what's going to happen, or if it's endothermic, not spontaneous, something like that, right? So it'll give some sort of hint so about what it is, exothermic, endothermic, say something about, you know, its spontaneity, and then you have to make some sort of conclusion from that. And so I don't want to give too much away, because otherwise I'll give away the question. Yeah, I'm giving you your rundown. But yeah, so for that question, I would say use this equation to kind of puzzle it out. You know, you have this chart to kind of help guide you with the puzzling. So that's my hint for that problem. The oxidation states, like I mentioned. We could do a review problem if you wanted, but we just have one of those like making a buffer solution when you mix like the salt and the acid. So that's just basically the Henderson-Hasselbalch.
Could you go more over the organic structure ones and specifically how you find the oxidation numbers based off the electrons? I don't understand that at all. I'll be very honest.
Yeah, let's
It
do
doesn't make any sense to me.
We're making a buffer, what was the name again?
the Henderson-Hasselbalch. Oh, let me go back. So,
Well, I guess a good thing, I guess, to keep in mind with those ones is like each element, you want to start with how many valence electrons that element has. Looking at the periodic table would be helpful.
yeah,
Knowing that sulfur has 6 valence electrons.
So let's try another organic one. Actually, I was like, I forgot what meth looks like. We should do meth. But.
I would say let's do like LSD or something like that, but those molecules are huge. So
Yeah.
It's like hundreds.
S H. All right, so let's try this one. And so remember the key was kind of pull apart every bond and then give the electrons to the more electronegative one. So that's how we treat all of them.
Hydrogen always has the plus one.
Usually.
I think
Almost
it
always.
can also have the -1.
Yeah.
Sometimes.
Almost.
Only if it was sodium hydride or like aluminum hydrides. So that's when you have the H -1. Or any other metal hydride.
Like alkali metals?
Yeah.
Okay.
Yeah, so you could go through, I mean, really all of the metals, because you could have like iron hydrides as well, or vanadium hydrides.
So like with this one, a good tip, I guess, is to remember the oxygen has those two lone pairs sticking out too. I forgot about that. The last one.
Yeah, so that's another, and same thing for the sulfur, right? So kind of remember how many bonds do they like to make? How many lone pairs do they have? Let me look at your exam. So I actually do draw out all the lone pairs on your exam, but yeah, I don't always do that, so I guess I felt nice when I was writing that exam. All right, so I kind of drew the results of what it would be if, like I said, you pulled apart every atom, and then we gave the more electronegative element the electron. So a little bit more explicitly than our previous example. And so then we can write our oxidation states. What's a nice bright color? And so let's just start with our oxygen. So write oxygen more electronegative than carbon. So I drew it, pulled off. So again, there's 2 electrons in both those bonds went to oxygen. So what's its oxidation state? -2. And just like Andrew was reminding us, so look back at our periodic table. So it's under our group 6. So 6 minus 1, 2, 3, 4, 5, 6, 7, 8. So that gives us our -2. So always look back, right, at how many valence electrons the neutral has. So then our carbon, I pulled it off here. So right, it got none from the oxygen, but then it wins over hydrogen, and then we split the carbon one evenly. So what's our oxidation state? So 1 plus, I'll write it on both sides so you can see. And then what does that leave? Hydrogen. So hydrogen's 1 plus as well. And so now looking at this carbon, so I pulled it off. So it loses to sulfur, so it didn't get those. It got 1 from carbon and then 2 from the hydrogen. So what's this carbon? So -1. And then our hydrogens, right, 1 plus again, that's pretty standard. And then what does that leave? Sulfur. So sulfur's -2, so write the lone pairs, and then at 1 over carbon and hydrogen. And then, of course, hydrogen on the end is 1 plus. And then you can add them all up as well in your head. Just verify, right, there's 0, so that cancels out, that cancels out. So it cancels all out to 0. And so just looking at your exam, so going back over what to expect. So we didn't practice writing a net ionic equation, so there's going to be a net ionic equation balancing in a basic aqueous solution, then identifying who's oxidized, who's reduced. There'll be some pH calculations, so it should be pretty similar to your titration lab. So going through like with a weak acid, so what's your pH initially? You know, what's your volume of like whatever base at the equivalence point? What's the pH after a certain point? And yeah, so basically what's the pH at 2 different points? And then we have the solubility product constant that we went over. We could do a practice problem. I have one prepared of figuring out what conditions a reaction becomes spontaneous, given it's a enthalpy and entropy, and then equilibrium dissociation like we did with Gibbs. So do we want to do a practice problem of the spontaneous one? Let's practice. So then a reaction has a change in enthalpy of positive 320 kilojoules per mole and a change in entropy of 101 joules per mole. So watch those units. So at what temperature? Does this reaction become spontaneous? Oh, yeah. So what equation do we need and what do we get?
So the equation that we need is delta G is equal to our delta H minus T times delta S.
And so I'll just star that one again, because remember that will be key for your word problem as well. And then, right, we can set this equal to 0, since we want to figure out what point it becomes negative. And then we can just plug in, so this looks good. And then we're solving for x, of course. And then I'm just going to work in kilojoules, because I don't like the big numbers. So I'll convert this to 0.101. So minus t times 0.101. And then algebra, so what do we get for our temperature?
I got 3,168.
So 3,168 Kelvin. And so I'll just type it out for a second. That's true. So right. And so make sure, right, you converted this to joules, or sorry, kilojoules. So it should be the 3,000. All right, we'll probably stop there for review, just so we can take our quiz, but then ask me questions during recitation. I know there are questions. And then if you need to take a break, feel free to take a break. I just thought I'd get the quiz going.
Like I'm starting to.
I did forget to say, so I'm doing another magic show outreach thing at Gold Hill this weekend, at the Gold Hill Library, I mean. And it's at 12:30 on Saturday. So if you want to be a student volunteer and join me, feel free to let me know ASAP. And I'll be giving bonus points out as well. That's still going on as part of the deal.